Okay, in this video we will check out the law of sines. So first off, when do we need it? Uh, we use law of sines in order to solve a triangle, whether it's one missing side or all the missing sides and angles of triangles that are not right triangles. So I have two drawn out over here, two examples. Those are not right triangles, right? I have a 120-degree angle in the first one and a 110 in the second one. They're obtuse triangles, or any triangle that's not a right triangle we often call oblique as well. So it doesn't have to be obtuse. All right, the two I drew happen to be obtuse, but that's irrelevant. We could have had acute triangles as well, where all three angles are less than 90. All right, for those that have taken a high school geometry, I wanted to explain first off a relationship that we've seen back then. And this ASA, AAS, SAS, SSS, in high school geometry, we use those to determine if two triangles were congruent. Okay, if two triangles shared any of those properties, a similar angle, side, angle in that order, or an angle, angle, side, angle, side, or side, 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 we proved congruence, okay, which means they were the same triangle. And here we're not doing that, but we're going to use that notation to describe what we have. Okay, so angle, side, angle. If we look at this first one I drew over here, we have in order an angle, then a side, then an angle. Okay, this meets angle, side, angle. Not congruence, but that's the information given. Where if we look at the bottom one, in order, we have like either side, angle, angle, or we usually refer that to as angle, angle, side. Although those are the same. All right, so that's the first two. Both of those are used. If we have that relationship, we use law of sines. The great news is that rather than memorizing if we need law of sines, or what I'll explain in another video for these two is law of cosines, is that if you try the law of sines when you have the information from law of cosines, it just won't work. Okay, you won't be able to do anything. So it's easy to remember which one to use because you try law of sines because it's kind of the easier one. It doesn't work, then you probably need law of cosines. I'm purposely skipping over this one here, SSA, or better yet, when I taught high school geometry, is just, are you really going to remember SSA or are you going to remember ASS, right? In geometry, ASS did not work. There was no AS in geometry to define congruent triangles. Now, law of sines, it could not work. So I'm going to do this one on a separate video. There are special cases of the ASS information given, and we'll have to look at that, all right, separately. It's worth exploring a few different cases. Alrighty. Now, before we use this, I do want to take a second of, alright, that's the formula, sine A over A equals sine B over B, or sine C over C, or reverse them, take the reciprocal, that's also true. It doesn't matter which one you use, just sometimes it's easier to use the one that you're solving, with the unknown in the numerator, but it really doesn't matter. They're the same thing. And we don't usually deal with an equation with three parts to it, right? Like two separate equals this, equals this, equals this. The point is you use the two that you need, okay? One other thing is often in trig we use Greek letters, so usually in triangles I stick with a capital A, lowercase a, like I did here. but some textbooks will only use that for right triangles. So if they use alpha for the angle, beta for the angle, and gamma, okay, that's ABC as well. Okay, that's just notation. We still deal with the alpha goes with lowercase a, beta goes with lowercase b, gamma goes with lowercase c. Okay, so what do I mean by that? Let's go ahead and draw first off where this comes from, and then we'll see how the formula is used. So if I have any triangle, not necessarily a right triangle, just any triangle. So I'm going to purposely try to draw a non-right triangle here. I would say that looks slightly bigger than 90 right here, right? We can label these sides, however, we'll just do A or alpha, right? B or beta, and then capital C or gamma, whichever variable you want to use. And then we usually call the sides opposite, just like in a right triangle, right? From alpha, we have lowercase a. From beta, we have lowercase b. From gamma or c, we have lowercase c. That's very important when doing this. Sometimes they will just give you the information and no triangle drawn, right? It's important when you draw the triangle, if you want to visualize what's going on, to keep that consistency. Okay, the A and the A are across from each other. B and C and C. Okay? All right. So here's the only trick, and then it's pretty straightforward from here. I am going to draw an altitude here. An altitude means a line from the vertex, from that corner, right, from that angle, straight down to a perpendicular, a 90. I could have done this off any, but that's the easiest one to visualize, and the results would be the same. And I'm going to call that altitude h, which stands for height. And that's common because usually when going off of a 90, right, that's our height. We don't really measure sideways like that. Okay. So now I have two right triangles. And now I could bring in old trig and say, well, from angle A, so I have opposite and hypotenuse. So from angle A, I have sine of A equals opposite over hypotenuse. I'm not going to mess with lowercase c in this example, but it can be done the same way. Well, I also know from B here, sine B, I have h over A, right? Opposite over hypotenuse. So if I solve for h, I now have two different equations. I have h is b multiplied by sine A, or h is a multiplied by sine b. Well, since these two are equal, right, they're both h, then I know these two are equal. Really, the law of sines could be left like this, but it's just cleaner, I guess. Like, we can get all the variables on the same variables on one side, like the same letters, to kind of clean it up, right? Like, if I divide both sides by a here, and likewise I'm going to divide by b, then I would have the b's would cancel, sine a over a equals sine b over b. We could do the same thing for the other sides to get the rest of the equation, like I said, but there you go. There's law of sines. Now let's use it. All right. There's where it comes from. Not too difficult, but I don't really want to do that every time. So let's use it. As we discussed over here, we have ASA, right? Whether it's given like this, if they said, we'll just call this capital A, this lowercase a, capital B, lowercase b, capital C, lowercase c. If they just gave you this information, whether or not you drew it accurately that's lowercase c, and that's often why they do use alpha, beta, gamma, because lowercase c, capital C, hard to discern in handwriting, right? But they'll often give units to like 6 centimeters or something. That's easy. You'll know which one is a side. But anyways, if they gave you this information, I would often just draw it, a random triangle. It doesn't even have to be to scale, to see what you do in fact have. Okay, if you drew it out, it would look like the triangle given. I know I have ASA and I know law of sines would work. The problem I'm faced with right now is my formulas, I either need, right, I need one unknown, and I can't really use, all right, capital A here, capital B here, and then lowercase c here. I would have 3 unknowns in a double equation. So this is an easy fix though. The angles of a triangle add up to 180, right? So even though I just have these 2, capital A and capital B, I do know capital C. It'd be 180 minus A and B, which is 145. So capital C is 35 degrees. Now I'm good to go. We can get the remaining sides, lowercase b and lowercase a. In this problem, we only need lowercase a. So I only need to do law of sines once. But if they wanted us to solve the triangle, we've seen these where it says solve the triangle. That means find all the missing sides, right? Well, I have uppercase C. I would still need lowercase a and lowercase b. But for this one, because x, right, is across from capital A, I only need lowercase a. So therefore, I am going to use lowercase a over sine A, sine of 25, equals lowercase c, 6 over sine C, sine 35. It all becomes calculator work. Multiply by this sine 25 on both sides. And you get A equals 6 times sine 25 over sine 35. When you plug that into your calculator, you get about 4.4. Okay, whatever unit we're in, you know, centimeters, inches, whatever. This problem didn't actually give a unit. Okay. All right, let's do one more. And this video is plenty long. So, again, we have AAS. I know that will work with law of sines. Again, I like to label everything because it's easier for me to visualize what part of these formulas here I want to use. So we'll just call this A, and then this one B, and this one C, which means across from A is A, across from B is B, and across from C is C. So I have capital B and lowercase b is what I want, and I have capital C and lowercase c. Therefore, I don't need this angle A. If it said, again, solve the triangle, easy to do. I mean, I can look at it. I know that's going to be 30, but I don't need it in this problem. All right. So again, we have, I'm going for lowercase b, and I have sine b, right? And then c sine c, that's the part of the formula I'm using. Again, it wouldn't have mattered if we did the reciprocals if I chose to do it this way. I just prefer to get my variable, my unknown that I'm solving for, that's my x, in the numerator, because then I have one step to solve the equation. Okay. Which brings me, I guess, looking at the first one, I said A is 4.4, which is actually x, right? That was my unknown. So I'm going to use x in this one. X over sine 40 equals 18 over sine 110. Make sure in this section your calculator is in degrees. So multiply by the sine 40 and just substitute all of this into your calculator. 18 times sine 40 over sine 110, and you get approximately 12.3.